Haskell Dependency Injection, fixing the CI/CD crash. Hey everyone, and welcome to this explainer. Today we're diving straight into part 197 of Ang's Haskell programming notes. We are going to tackle something I know we've all faced at least once, a developer's absolute worst nightmare. You know the one? A bug that runs flawlessly on your local machine, but literally crashes the very second it hits your deployment server. We'll see exactly how applying a classic software design pattern fixes this whole situation elegantly and completely. The code works perfectly on your machine, so why does it crash in the CI/CD pipeline? It's a universally relatable scenario, right? You've written this open ebook function in Haskell. You compile it, run it on your laptop, and boom, it works perfectly, opening your files right on cue. But the second you push that code and it hits the automated testing phase on your deployment server, it just crashes immediately. Why does this happen? Well, the original test code was trying to blindly execute an external OS command. In a local development environment, your system knows exactly what to do with that. But servers, they operate under vastly different conditions, and that gap is exactly what triggers the failure. We're looking at a local development environment equipped with GUI tools up against a CI/CD headless GNU Linux server that completely lacks them. Let's break this down a bit. Locally, you are fully equipped with graphical tools and display servers, so you can visually open a file like an ebook with zero issues. But your CI/CD pipeline? That is typically a headless GNU Linux server. It doesn't have a screen. So when your open ebook function fires off a hard-coded system command expecting a graphical interface, the headless server simply doesn't have the tools to process it, and that results in an immediate hard crash. So the solution takes 3 distinct steps. Remove the hard-coded call process, parameterize open ebook with a runner, and finally, pass the process launcher as an argument. How did Ang actually solve this? Well, definitely not by trying to hack GUI tools onto a headless server. Actually, scratch that. That would be a total nightmare. Instead, the fix involves fundamentally rethinking the function's design. First, we just entirely rip out the hard-coded reliance on a specific system process. Second, we parameterize the open ebook function with a variable we'll call a runner. And third, instead of assuming we know the environment, we pass the actual process launcher as an argument when we call the function. By decoupling the action from the hard-coded system command, we gain total flexibility over what happens in different environments. We're essentially taking a line that said result:(try call process cmd args and swapping it to result:(try runner cmd args. Think about the logic shift here. The old code directly invoked system.process.callProcess. That command was physically welded into the function's logic. By removing call process and swapping it out for our injected runner parameter, the function no longer dictates how the command is executed. It just safely delegates that job to whatever runner we decide to provide it. It's like swapping out a hard-coded, unmovable engine for a universal plug. Dependency injection is the act of parameterizing a function by passing a dependency, like a process launcher, as an argument instead of hard-coding it. The absolutely crucial point here is that this simple code substitution is a perfect, highly practical example of dependency injection in action. Instead of a function building or hard-coding its own dependencies inside its body, you supply, or inject, the dependency from the outside, in this case, our external process launcher. By injecting it, we can pass a real OS launcher when we're running locally and a fake, completely safe dummy launcher when running automated tests in our CI/CD pipeline. The function behaves identically, but the crash? Bypassed entirely. So our updated type signature reads, open ebook takes a function of string to a list of strings to IO units, and a file path, returning IO either app error, IO units. Now, we're in a statically typed language like Haskell, right? So changing a function's parameters inherently means a brand new type signature. And yeah, this block might look a bit intimidating at first glance, especially with those nested parentheses and multiple arrows. But I promise you, it is incredibly logical once we parse out exactly what is being asked of that new runner argument. Let's map out that new runner signature piece by piece. Row 1 is our string. That represents our command or executable name. Think standard OS commands like xdg.open, open, or cmd. Next, row 2, the bracketed list of strings is simply our list of argument strings that get fed directly into that command. Finally, row 3, this resolves to io.o. In Haskell, as we know, this means it's an IO action that performs side effects like interacting with a file system, but returns absolutely nothing, otherwise known as unit. It's really all about moving from the input type on the left to the output type on the right. To fully understand how these types connect, we really have to look at the function arrow. It acts as a strict symbolic operator representing a transformation. It takes an input type on the left and transforms it into an output type on the right. In the context of our dependency injection, our runner takes the command string and the list of arguments as inputs and brilliantly transforms them into an executable I/O action as the output. It is a super clean, mathematical way to guarantee our injected dependency takes exactly what it needs and does exactly what we expect. So now that we have a testable, injected external process call, how do we actually write the test cases for this refactored function? Which brings us to the ultimate payoff of this architectural shift. The deployment roadblock is completely gone. But it leaves us with a brilliant puzzle. How exactly will we write the test cases for this refactored code? How do you construct a mock runner to satisfy that type signature without triggering a real OS command? Well, it's a fantastic problem to ponder. Until next time, thanks for joining me for this explainer.